Yeah, hello, welcome everyone to this week's ENLA seminar. And it's my pleasure to introduce Edgar Solomonik to this week's seminar. Edgar has been an assistant professor at the University of Illinois at the computer science department for a couple of years now. And he leads the research group on parallel numerical algorithms. Edgar did his undergraduate at the University of Illinois and then moved to UC Berkeley and did his PhD with Jim Demmel on, I have to read that out, provably efficient algorithms for numerical tensor algebra. You might know about this work because he also received the Householder Award for this work. He then moved on to do a postdoc at ETH Zurich and is now an assistant professor at the University of Illinois. He received a couple of several awards. The Householder Award I already mentioned, but he's also received the SCIAC Supercomputing Early Career Prize. Is well known for his work on parallel algorithms and tensor methods and tensor decompositions. And today he will talk about some of his work on optimization methods for tensor decompositions. And you see the title there. We look forward to your talk. A couple of announcements. If you would like to ask a question, any of the audience, please raise your hands or make yourself identifiable on the chat. And I think Edgar will break a couple of times so we can have the questions being asked. Thanks.
Thanks, Melanie, for a very kind introduction. And thanks to all the organizers for inviting me and also for organizing this whole series. It's been a wonderful resource to also point students to and to kind of attend and see what's going on during the last couple of years. So today I want to talk about essentially three results, which have been led by three different PhD students from our group, the Laboratory for Parallel Numerical Algorithms. The first project I'll talk about is about efficient solvers. So kind of it's a direct / iterative solver for interior point systems. And this is something that was led by Samad Karim. Then I'll talk about Tucker decomposition. So I'll switch to tensors for the last two parts. And we'll talk about the use of randomized methods for constrained linearly squares problems that arise in Tucker decomposition. And finally, the last part I'll talk about is actually a new method for CP decomposition, which has some really interesting features. In particular, it achieves high order convergence to exact solutions while having really no additional cost over ALS. These are all really new results, so I'm kind of excited to talk about some of these things for the first time today. In the first part of the talk, I will talk about interior point methods for constrained quadratic programs. So here we'll consider a Hessian matrix H, equality constraints defined by matrix A, and inequality constraints defined by matrix C. These types of QPs arise in all types of problems, but they have been especially studied a lot in the context of numerical PEs and kind of interior point methods in this context, where H and A have a particular sparsity structure. One can also reduce general nonlinear optimization problems to quadratic programs of this type by methods such as sequential quadratic programming. So this also provides a pathway toward general nonlinear optimization. So what we'll focus on is actually solving the linear systems that we get once we try to solve such a problem with interior point. We can derive that linear system by considering the Lagrangian function and then deriving from it the KKT conditions, which largely concern this gradient. These conditions are then augmented by when considering the interior point method by introduction of slack variables and kind of a centering measure. These can also be derived by kind of introducing barrier parameters. But this is a particular flavor of interior point I'll talk about today, and it's a fairly standard approach for this type of problem. So here we introduce the diagonal matrices S and V, with the product of which will be denoted later throughout the talk as D of K, where K will be the iteration number of the interior point method. And these are essentially the parameters that interior point is adjusting throughout execution. And that's the part of the system that kind of becomes ill-conditioned. So as we kind of approach convergence, we're trying to turn our barrier into a more and more sharp function And this is leading to kind of large variations in the values of SV, which is in general positive, but can be quite ill-conditioned. So if we can write down these conditions in terms of a linear system of equations with the following matrix, where the S and V parameters here in effect appear in a final block. And so we need to solve this type of system at every iteration of the interior point method, which here is denoted by index k for the iteration number. So the standard approach to solving this type of system is, in a sense, to eliminate the mu variables first by kind of absorbing this dk block into H, and then solving this reduced system, or just working with this original system and trying to solve this either iteratively or via direct methods. The basic idea of the method that I'll talk about and kind of the approach that we've been investigating, which as far as we know is kind of new, is to instead consider factorization of the part of the system that's fixed throughout the interior point iterations, so of H, A, and A transpose. And then to deal with the rest of the system by solving it iteratively at every iteration. So we'll compute a single factorization of a matrix throughout the entire execution of the interior point method, as opposed to trying to refactorize the matrix each time, or to start from scratch with an interior point method, with an iterative method at each step. In doing so, we are making some assumptions. In particular, we will want F to be full rank. And for simplicity, I'll also be assuming that H is positive definite, although we generally want to consider semi-definite H. And I'll return to talking about that limitation a little bit later. And so to say a little bit about what has been done in the literature for these types of systems. So these are kind of very well-studied block-structured systems that have kind of arise from a number of problems in the numerical PDEs. The particular problem we were looking at, that the application we were looking at that led us to kind of study these types of linear systems was an optimal control problem, where kind of you do a discretization that leads to generally a banded structured system plus additional terms. And so this is the type of problem that you might get and try to optimize with an interior point given a discretization. So there's been a lot of work in solving the linear systems, primarily for the reduced 2x2 system, or just for the original 3x3 system. And there have been preconditioners that have been designed that often try to specifically exploit this block structure that we see in the system. So here I'm citing just a few papers, but there's many other works and many other preconditioners that are relevant for these systems. But kind of, I think recently it's been shown by Marini, Solomonik, and Tani that the 3x3 system can be kind of better conditioned than this reduced 2x2 system, in a sense because we're taking this ill-conditioned matrix D and kind of factorizing it first and absorbing it into kind of a key part of this reduced system. However, kind of from an experimental point of view, the 2x2 system is still competitive. So returning to the method we're proposing, again, what we want to do is to first factorize F and then iteratively solve the reduced system that we get after eliminating the variables associated with F. And that's of this form, where the interior point variables D, this diagonal matrix here, is up front, and then there is this other term. So we can expand this term in terms of the writing down the explicit inverse of F if we assume it's invertible in the following form. And we can then kind of observe that this term here, H minus H sub A, sometimes will be lower rank, or sometimes this H sub A term will be lower rank. And so this will allow us to design efficient preconditioners for this reduced system. But perhaps the more basic observation is that we've been able to pull out this ill-conditioned term to the front of the system. So the main goal of our preconditioners will be to alleviate the ill-conditioning associated with this term. So the basic preconditioner we'll propose will simply be this diagonal matrix, which has to be positive definite, so it's invertible. And the more non-trivial preconditioner we'll propose will have to do with the case when H minus HA is relatively high rank, and we want to keep the HA component. So in particular, we can rewrite HA as QQ transpose HQQ transpose, where Q is the orthogonal factor of the QR decomposition of A transpose. And this kind of shows us that H minus this term will generally be kind of close to 0 in low rank if Q is close to square, which is this case. And this term itself will be low rank if Q contains only a few columns. So then we can absorb Q transpose and Q here, and absorb that we kind of have a low rank factorization. So this is useful because we now know that, in a sense, our matrix is described by something that's diagonal plus low rank, or with an additive term, we get something that's low rank in this other regime, other extreme of constraints relative to number of variables. So we'll design preconditioners then that are specifically targeting the regime when there's a low number of degrees of freedom, namely the difference between the number of variables and the number of equality constraints, and another preconditioner which is for the high degree of freedom case, which you can think of as approximating this term, but it's perhaps yet better to think about these preconditioners as trying to turn KF into something that's identity plus low rank. And that's exactly what these accomplish. So if we kind of perform two-sided preconditioning with these to preserve symmetry, which is kind of equivalent to doing the one-sided thing when you actually evaluate it in execution, we see that we get rid of this leading term dk, and instead are left with simply this remaining term, which in both cases we can show is bounded in rank. So this means that this matrix will primarily be composed of eigenvalues that are equal to 1, plus whatever the rank is of that term in terms of non-unit eigenvalues. And if we can bound the number of eigenvalues in these matrices, we can also bound the number of conjugate gradient iterations. So these preconditioners directly give us bounds on the complexity of CG and exact arithmetic. And we also kind of have hope that the resulting terms will be better conditioned, because we've, in a sense, eliminated dk from this leading term, although we have multiplied this other term by something that is related to the interior point parameters. So in general, we do not have a completely clean bound on the condition number of this object. Okay, so to kind of summarize the high-level picture of these methods compared to standard approaches, we start with factorizing this matrix F before we start the interior point method, in a sense. Then we proceed with interior point method iterations, and we construct a preconditioner that's either low degree of freedom or high degree of freedom, depending on the kind of number of equality constraints in the original problem. Then we need to factorize the preconditioner, and the preconditioner may change at every step since it involves dk. And then we iteratively solve the reduced system equations, where we leverage the factorization of f to perform a solve with f at every iteration. So we will not form kf explicitly. We will instead simply solve implicitly with f and take products with this. While in the standard method, what we would do is to, for example, form an augmented system, consider a preconditioner among choices that are respecting the block structure. Common among these are constraint preconditioners, which preserve the A blocks, so these off-diagonal blocks, and then use some diagonal matrix or block diagonal matrix approximation of this 1-1 block. Another type of preconditioner that's been received a lot of attention in literature is kind of block diagonal or block triangle. You can also have an up-diagonal block here, but primarily this is the form where that people have also paid a particular attention to. But there's a lot of flavors of these, and I'm just giving a couple of examples here. So then we need to, again, factorize the preconditioner and then perform iterative solves where we have explicitly formed KD, so we're simply taking matrix vector products. We don't really need to do solves with F. So one potential overhead of the method we're proposing is that you do need a factorization with which you can solve efficiently. But if you perhaps invest time into factorizing F in a way that allows for efficient triangular solves, this may pay off. And there's also the limitation that we've assumed that we can actually invert F, which is not generally the case. So there are examples of QPs of this type where F will be singular. And we also generally want to consider the case when H is semi-definite, which may cause F to be singular, but does not necessarily imply that F will be singular. So an example of when H is semi-definite is when we simply have some variables in the quadratic program that are only linear, kind of in our objective function, as opposed to quadratic. So we first of all assume that we can factorize f, and the other problem is that our high degree of freedom preconditioner actually had an H inverse in it. So if H is a semi-definite, this is a problem, even if f is invertible. A quick fix to this is that one can in principle use regularization to always ensure that H will be semi-definite and consequently f will be non-singular. Sorry, not SPD. But there's also, but we're working on developing adaptations of this approach to the other cases. In particular, there's kind of at least two major cases we can consider. One is when H is semi-definite, but overall f is non-singular. F also contains A, and in a sense that matrix A can make the overall matrix be non-singular. In this case, we can still kind of factorize f. We just need to perform pivoting. And we can actually still have a high degree of freedom preconditioner. We just need to use a more complicated derivation and get a term that is somewhat more complicated to compute. The harder case is when both H and F are singular. And in this case, we are working on an approach that essentially does a rank revealing factorization, or simply looks at the structure of the matrix and notices, okay, I have 0 blocks corresponding to linear variables, and then pivots those to the end of the matrix, so essentially to the block that will also have decay, so that part of the system is not factorized. But we have not fully evaluated these methods yet. And the other kind of major question that I've already mentioned on the previous slide is, how expensive is actually this method in terms of cost? And that's something we'll kind of attempt to provide, to quantify by using cost models and trying out the method that we proposed on a whole bunch of different test problems. Although we'll for now assume that H and F are SPD, and for the test problems that we tried, if H was not semi-definite, we would regularize H. But first, let's confirm our kind of theoretical results regarding the convergence of CG. So here we consider synthetic problems where we change the number of equality constraints M1 for a fixed number of degrees of freedom. And then PLKF here is our low degree of freedom preconditioner for the reduced system. This is the high degree of freedom preconditioner, and this is simply the unpreconditioned system. And what we're plotting is the CG iteration count averaged across IPM iterations, where kind of the distribution across IPM iterations is kind of shaded for each type of preconditioner. And here we also have kind of the theoretical bounds that we've derived. And we generally see that the preconditioners achieve the predicted number of CG iterations, except in the limits where we're kind of using the wrong preconditioner, in which cases what we can realize is that essentially the problem is round-off error. The preconditioner is no longer actually improving the condition number in this regime if we plot the condition number. And so the number of iterations is actually above the theoretical bound due to additional round-off error, and actually worse than the unpreconditioned methods. But overall, we are substantially able to reduce the iteration count relative to the blue dots, which are just the unpreconditioned methods, especially in these extreme cases when the number of degrees of freedom is either quite low or quite high. Okay, we can also consider the condition number obtained for a lot of different test problems for the preconditioned reduced systems. And this is a lot of numbers, but here blue is good, so this is a logarithm of the condition number, and we want small numbers. And the last two columns are the low degree of freedom and high degree of freedom preconditioned reduced systems. This column is the unpreconditioned reduced system that we are considering. So relative to it, we tremendously improve the condition number. So kind of this decay, sorry about that, was the critical problem there. And we also compared to two other preconditioners that work on the original system and not the reduced system that we consider. And we see that those are sometimes and generally able to reduce the condition number, but not by as much as we are. So we generally win for condition numbers by quite a bit across a range of problems. But on the other hand, we have done a lot of work in the sense that we require factorization of a large part of the system in order to get this conditioning for the reduced system. We can also compare the speed up obtained by our preconditioners with respect to the best of an unpreconditioned method, a method with a constrained preconditioner, and a method with a preconditioner from a paper by Tim Rees and Chen Greif, which is block diagonal. And so here we are plotting the logarithm of speedup. This is a little bit of a weird plot, but the one I like because you can kind of look at the area that's above 0, and that's where we're doing better. And you can compare it to the area that's below the 0 line. That's where we're doing worse. And we can kind of see by how much we're doing better. And the relative improvements are, in a sense, larger than where we lose. But on the other hand, it's clearly the case that this is not a method that's always the method of choice. It depends on your linear system and kind of the relative cost of solving with f, factorizing f, as well as factorizing these other preconditioners. For example, the constraint preconditioner is not cheap to factorize and is quite expensive in some cases. And here we've excluded the problems for which direct solve is actually the fastest method. But our preconditioned methods are also competitive relative to that, which is the best for some of the problems, but not most of the problems. So that's kind of the end of the first part of my talk, where we've presented, in a sense, a strategy for solving interior point systems that tries to reuse the same matrix factorization and also tries to forms preconditioned systems that are well conditioned in theory and also in practice. And we have a paper on this that's recently appeared in arXiv if you want to take a look and see more details. But also, if there's any questions now, I'm happy to answer.
I don't see any questions, so I think you can carry on.
Okay, thanks.
Thanks.
Okay, so now we'll switch to talking about tensor decompositions. I'll talk about two types of tensor decompositions. One is known as Tucker, and the other known as the CP decomposition for Canacom parafact or canonical polyadic. With the Tucker decomposition, we can think about it as a core tensor of the same order as the tensor we're trying to factorize, multiplied by a factor along each mode, where the factors have orthonormal columns. Well, for a CP decomposition, we in a sense have a collection of rank 1 tensors, so a collection of tensor products of vectors. And we can kind of think about it in terms of factor matrices that correspond to these collection of rank 1 components for each mode of the tensor. And throughout this part of the talk, I'll have in mind a tensor that's has dimensions equal to S, and the rank will usually be denoted by R in respective settings. Among the most common methods for optimizing for these decompositions are alternating schemes, which in a sense fix all except some of the variables, some of the factors, and try to find the best choice of the remaining factors, which is, if you kind of work it out correctly, a quadratic subproblem. So for the case of Tucker, the standard method for doing this is called high order orthogonal iteration, HOI. And you can think about it as actually fitting one of the factors and the core tensor all at once. So it's finding the best choice of the product of some core tensor and some orthogonal lower rank factor so as to minimize residual with the other two fixed. And so we can think about that as a linearly squares problem with a rank constraint. So we want the solution to have a low rank. What's nice is that this linearly squares problem consists of equations that are a tensor product of two orthogonal matrices, and hence the equations are themselves orthogonal. So we'll actually be able to solve and then truncate, which is the usual implementation of HOI. In the case of CP decomposition, there's a similar algorithm that's kind of, I think, still the state of the art today, which is CP-ALS. And again, is an alternating least squares scheme where we fix two factors at a time. Here we fixed B and C, and are optimizing for the third factor, here A. So here our linear equations will be defined by a Cauchy-Rao product, which is an outer product of each column of B and C, concatenated all together into kind of a column vector-like matrix. And this T1 here is an unfolding of the tensor T along the first mode. So this gives us a matrix that's column vector-like after we do the transposition. So we'll be talking about, in a sense, how to accelerate this solution to this HOI problem by sampling. And then we'll also talk about how to do CPD, both leveraging Tucker as well as be an altogether different alternating update scheme. So if we look at the cost of these iterations, you can perform both of them by iterating through the tensor and kind of multiplying it by the parts of the factors that we need in order to compute these equations. And that comes out to be essentially something that's proportional to the number of non-zeros times a polynomial in the rank. So for HOI, this becomes R squared if you do it carefully, while for CPALS, this is always R. But also the cost is bounded by the overall size of the tensor as cubed of the dense tensor times R. And generally, one can observe in practice that HOI converges very quickly, especially if you initialize it with what's known as HOSVD, which is kind of taking SVDs of the unfoldings of the tensor. But even without that, it converges very rapidly. Well, for CPALS, we kind of an unknown problem is that it kind of tends to fall into swamps where it suffers from very slow convergence, even for relatively well-behaved problems. So the main result I want to talk about for HOI is a sketching scheme that allows us to, in a sense, have execution time that's linear with the number of non-zeros in the tensor, plus the dimension times some polynomial in R. So overall, we perform very little computation relative to the tensor size and are actually linear in the mode size, which means we can handle extremely sparse tensors. So this algorithm is, I guess, particularly attractive for scenarios where you want to do a low-rank Tucker decomposition of a highly sparse tensor, perhaps with also noise, so the accuracy is not the most important thing, and sampling is a good idea. But in fact, we'll see that with a large enough sample size, we can attain extremely high accuracy also with these randomized methods. And by accelerating Hui, we'll actually also get a method for performing CP decomposition for a lower rank CP decomposition. And the way that can be done is that if you have a Tucker decomposition and you perform a CP decomposition of the core tensor, you actually recover a CP decomposition of the original tensor. And this works quite well. In the exact case, it's exact. In the approximate case, it gives you a very good approximation. So if we want to do CPD, what we could do is to first do HOI with sampling, obtain this core tensor, perform a CP decomposition of the small dense tensor, and then from that recover a guess of the overall CP decomposition that is often quite good. Okay, so let's then look at what we need to do to actually perform sketching on HOI. So typically what's done with HOI is that we solve our linear least squares problem for the best choice of P. Then we perform an SVD to subdivide it into the factor and the core tensor. And this best rank R approximation gives us what we want. So the main idea of the sketched algorithm that we're proposing is very simple, is to perform sketching on kind of the right-hand side and the equations here. And only after that, having computed the solution, perform a rank R approximation. So here S is some sketching matrix, and for our results, there's multiple types of sketching matrices that we'll do. In general, a condition that we need is that actually the Frobenius norm of these terms is not too different. So where here we've inserted the approximated x1 and a. And so the main question is, if we, in a sense, do sketching for this linear least squares problem and then do a rank R approximation, what does that do to our error bounds and our and the respective sketch size? So our work is kind of most closely related to an algorithm known as tensor sketch, which is performing Tucker decomposition with sampling, except it's optimizing for a single factor at a time, which is not a constrained linear least squares problem, but a plain linear least squares problem. And that allows it to kind of efficiently leverage sampling and obtain a good accuracy. but you get something that's less accurate than HOI is because you're only optimizing one factor at a time. HOI is kind of the standard scheme for Tucker for a reason that we'll see from also our experimental results. So coming back to the sketching matrix, what we need is that it satisfies this 1/2 delta epsilon accurate sketching matrix property, which in a sense means that it kind of projects everything while keeping the singular values not modified by too much. And the main result that we get is that the sketch size that we need to obtain an epsilon level of accuracy is going to be 1/epsilon times larger than the sketch size that's usually needed for a linearly squares problem that's not constrained in this way. So the need to do truncation does cost us an accuracy in this case, but as far as we've seen, not been able to prove this bound yet. So to summarize those sketch bounds, so as I mentioned, the tensor sketch algorithm that was published by Malik and Becker in Europe 2018 is in a sense finding the best choice of either a core tensor or one of the factors at a time and doing sketching on this linearly squares problem. While we instead consider sketching of this, in a sense, rank constrained linearly squares problem, where we first sketch, then solve, then truncate. And we can show that the sketch, and we've been able to prove sketch size bounds both for the sketch used in the tensor sketch paper, as well as for kind of the standard, the more standard technique of leverage scores. And leverage scores for this matrix are quite easy to compute because they're simply the products of leverage scores of the factors, since they're already orthogonal, and a leverage score is, in a sense, the norm of a row of an orthogonal matrix. And so what we see is, in a sense, we get a sketch size that's a factor of epsilon worse than tensor sketch that optimizes only for one factor at a time. But we have this algorithm that's somewhat more robust. And so we can try to compare those in terms of experimental results. And so to kind of summarize the overall algorithm first, in general, we should start by a procedure called randomized range finder, which we can also for which we can also employ sampling, and which allows us to compute an initial guess. And so this is, in a sense, a sampled SVD of an unfolding of the tensor. So we want to find, in a sense, the left singular vectors of a row vector-like matrix. And we can do that in an approximate way, and from that obtain a robust initialization. This is important, especially for tensor sketch, as we see for leverage square sampling. It's robust to also just starting with a random guess. But this ensures that, in a sense, we've captured large components of the tensor so that when we actually proceed with sketching, we don't miss out on anything completely, since the sketching is based on the factor matrices, which define the linear system. So then for each factor and for each iteration, we build the sketching matrix, we perform the sketch on the tensor, and then we perform the sketch on the actual linear equations that we need to solve with. Then we perform the solve and truncate to obtain the result. So it's a simple modification of the standard HOI algorithm. All right, and so if we look at the results, here we compare standard HOI to HOI with leverage square sampling to HOI with tensor sketch style sampling. And then we compare it to the referent tensor sketch algorithm, which is not really doing HOI, which is just optimizing for a factor at a time. And we see that for fairly kind of small tensors with some collinearity, the randomized range finder, first of all, is helping, but also in general, the two methods that we propose that approximate HOI are achieving a level of fitness that's close to the baseline HOI and a lot higher than the reference tensor sketch method. We can also kind of see this with respect to sample size, that for a fairly modest sample size K here, we're able to converge to the HOI baseline fitness with leverage score or tensor sketch based sampling. Yeah, and here again, we see something similar. So for, we also have more robustness than this TS reference algorithm in that the objective has less fluctuations across sweeps of the method. And this is the details of kind of the tensor we tested on here, which is in a sense designed to have some large components which throw off kind of naive sampling methods. Okay. And we can also leverage this, as I mentioned, to do CP decomposition. And here, if we just look at the number of sweeps and what that does to the CPD fitness, where in a sweep of this Tucker plus CP method, we're computing this a Tucker decomposition, which HOI, and then performing a CP decomposition of the core tensor. And we see that kind of the Tucker plus CP method, which is the orange line over there, converges to a high fitness faster than what would be achieved by the ALS method, which is here denoted by CP, or leverage square sampling done for the ALS method, which has also been done in literature in the past. So at least in terms of sweeps, this converges a lot faster. And when we add leverage square sampling to the Tucker, we do just as well in terms of fitness as the baseline method performs for this tensor. That's all I have for this part of the talk. Are there any questions?
Yes, there are indeed. There are also a couple of questions that came in on your first part of the talk, so maybe we start with that. And they were related to the inversion of that 2x2 block, this F matrix that you were talking about. So first unmute Eric Bowman so you can ask the question yourself. Okay.
Hello, I think I found the unmute now. So thank you. My question was, you used a direct solve for this 2x2 system, the F matrix, and I'm thinking for large problems, this will be impractical. So could you use an iterative solve? Because presumably this is, reasonably well conditioned.
Yeah, I think the problem is then you have kind of nested iterative solves, and so then you have to pay the square of the number of iterations. So, but something like that could be explored, but it does seem bad in the sense that for every iteration here, we need to apply F inverse. So if you want to apply F inverse iteratively, you need to kind of do that for each iteration of this outer method. But that, I think that could be in principle explored. So I guess my kind of intuition was that sparse direct solves are also often an attractive approach, even in the kind of large scale setting for these interior point problems, because they're so ill conditioned. So somehow what we're doing is, partially a direct solve and partially an iterative solve, and it's kind of somewhere in the middle of the spectrum.
Okay, and a related question, I'm trying to unmute Michael Saunders, but I can ask it myself. So that's related. So do you use the an LDL transposed factorization for that direct solve?
Right. So if we just assume H is SPD, we can just use Cholesky, and our experiments so far have just done that. If you don't assume that, I think the appropriate thing to do will be to use LDL transpose with pivoting.
Okay. Thank you. And then we've got some questions on the second part of the talk. Let me just unmute Patrick so he can ask his question.
Okay. Hello, can you hear me?
Mm-hmm.
Okay. Yeah, I have a question about the CPD algorithm and this value of capital R. So the tensor rank, the number of rank 1 terms. Do you know this in advance, or is this given somehow?
Typically something that kind of the user has to ask for and select. So in a sense, I guess there's two settings, and I'll distinguish these a bit in the third part of the talk, is perhaps you want an exact decomposition, and there perhaps you can try different Rs, but often you want just some low rank approximation. And one of the reasons people look for low rank approximations is often to kind of do high order principal component analysis. You actually want to look at the factors and kind of think about what they're doing. And which is in a sense, in that case, R might be kind of really dependent on what you're looking for. And in general, you can't relate very well decompositions with high R to those with low R. So if I have some true underlying rank and I do a low rank approximation, the best a low rank CP decomposition will have factors that are generally unrelated to the overall true factors that are of higher rank. But yeah, there's also kind of a bunch of variants of the problem to consider that are of varied importance. For example, the case when the rank is larger than the dimension is especially important both for exact decomposition, because that could lead to discovery of fast bilinear algorithms. So the fast matrix multiplication problem is essentially tied to decomposition of a high rank tensor. And also there's applications that want a very high accuracy approximation and are willing to have high rank. This is the case, for example, in quantum chemistry methods. So kind of there, you just want kind of art to get you as much accuracy as possible, and you can perhaps tune it based on that. But it's relatively difficult to transition for these methods between different values of R because there's no relationship between those approximations.
Yeah, okay. But if you speak about approximation of your tensor by such a rank 1 sum, I'm not exactly sure if then the term canonical is really correct there. If you just approximate your given tensor, canonical means it's an exact representation in a certain number of rank 1 terms, right? Which is pretty difficult.
Yeah. You can think of the exact decomposition as being an.
Yeah, then it's okay. And just maybe a small follow-up question, unless you are going to talk about it in the remaining slides. Have you also compared your CPD algorithm to like other like optimization based algorithms for computing a CPD?
We have not in this. In this case, we compared to, for example, leverage square samples for CP, since this was one of the most closely related works. We also have a recent paper that did an in-depth study comparing Gauss-Newton.
Yeah, that's what I meant. Yeah.
To ALS, and there we've been able to show that Gauss-Newton can outperform ALS, both in terms of accuracy and in terms of time to solution, but not uniformly. And there is kind of major caveats everywhere there. So I still feel to a degree that ALS is a reasonable baseline method in a lot of settings. There's kind of improvements proposed, but they don't necessarily lead to kind of uniform improvements for many problems. Yeah, that would be my summary of that. Yeah, but there's also a lot of methods out there that one can compare to.
Okay, thanks.
Okay, thanks. You can carry on your talk.
Okay, thanks for all the questions. Interesting questions. Okay, so and this last part of the talk I'm kind of very excited about, and this is something that has been what we've been really focused on over the last few weeks and months, but really we initially encountered this method about a year ago. So I'm quite excited to talk about it for the first time. In a sense, if we look at the CP decomposition and the alternating least square scheme, so here above, this is the form we'll use to denote a CP decomposition, and this is the element-wise equations that define it. What ALS does is it successively minimizes the residual error by essentially finding the best choice of A, B, and C. And we can write that as the following update. So in a sense, the linear equations are given by the Cottrell product of C and B. And so what we want to apply to T is their pseudo-inverse. So the update that we propose to do instead is to take the Cottrell product of the pseudo-inverse transposes of these two factors, which is generally not equal to the pseudo-inverse of the Cottrell product of the factors, but it is a left inverse of this. So it is a left inverse of C Cottrell product B. However, generally one should not really think about this as an approximation to this. It is really something that is different and as we are finding quite interesting. So in particular, the most basic feature that makes this method kind of pop out is that if we consider exact decomposition for low rank, so for R less than in dimension, so ALS for this problem, like in general, for general approximations, achieves a linear convergence rate. And we could achieve higher order convergence by something like Gauss-Newton, but that requires optimizing all the variables at once and not just doing an alternating scheme. And so kind of a single iteration of Gauss-Newton is quite expensive. The proposed scheme is actually high order for this problem, and it's very high order. If you count the order of convergence per sweep, it's actually at least quartic, and the order increases with the order of the tensor. The order of convergence increases with the order of the tensor. Generally, we can say the order is alpha, where alpha is the positive root of this polynomial for each update. So for every alternating update to each factor. And this formula, it comes from the fact that in a sense, the error will be the product of all the errors to the other factors. And if you look at that recurrence, that's kind of in the order 3 case, the same thing as the secant method for nonlinear solve, where the error is the product of the two previous errors in your convergence analysis. And that gives you a convergence rate that's like the golden ratio, which is also the case here. But because we have a number of subsweeps per iteration, the overall convergence rate is actually the nth power of that. And this is how we get a quadratic order, even for order 3 tensors. While the cost per iteration of the update that I showed you is roughly proportional to ALS. So you need to perform a pseudo-inverse, so perhaps a QR factorization of each factor, and then you just need to do an MTT-KRP. And you can also use things like dimension trees, and you can leverage sparsity of the tensor in all the same ways in ALS, and you get this convergence. And as I mentioned, the reason for this is that in a sense, we can associate the error in the update given relative to the true factors, if we assume that we start close enough to them, by the product of the errors in other factors. Except we have to be careful about the column scaling of the A factors, but the column scaling is kind of not important for ALS because you can push it into any one of the factors. So what we see is that modulo column scaling, the error will scale as the product of the other errors. And to see this is quite easy, actually, unlike the convergence proof of general ALS for kind of not necessarily the exact decomposition. In this case, we can simply plug in the true decomposition of the tensor into the update rule. And then what we observe is that kind of the factors, the pseudo-inverses by which we're multiplying, get respectively multiplied by the true factors. So here, A tilde 1 is the computed approximation to A1, and A tilde 2 through A tilde n are the approximations to the factors that we currently have, so our iterates. And so in a sense, we're annihilating the true factors in the true decomposition and applying these pseudo-inverses. And so when we do this, if we assume that our kind of decomposition is close to the iterate, we can insert that in and observe that we get a diagonal matrix minus something that's proportional to the going to scale with the norm of the error, Hadamard product, all the other terms. But a Hadamard product with a diagonal matrix is again a diagonal matrix, so we can collect all the cross terms here except for the products of the error, the delta related terms, into a diagonal matrix. And then if we look at the rest of the terms, their norm will scale with the product of the norms of these error terms. And that's, in a sense, the main thing we need to show convergence for the exact case. And if we look at what happens in practice for exact decomposition, these lines are ALS for different order tensors for some simple random exact problem with rank equals to 20. This is a 100 by 100 by 100 tensor. And these are what here is called the mnor method, so this new iteration scheme we proposed. And as you can see, it's converging extremely fast once it actually finds a solution, although it's not in general minimizing the residual in a monotonic way like ALS does. And so if we consider a tensor that is somewhat more, has a more ill-conditioned decomposition, then the ALS is doing yet worse in linear convergence rate, while this method is still converging in 10 iterations to the exact solution. So far, everything I've talked about, though, has assumed that the rank is less than the dimension and that the true factors are full rank, and those assumptions are kind of coupled. If you go to rank greater than the dimension, we can still generalize our method to that case, and it performs well, but it doesn't necessarily achieve, quadratic convergence to the solution. Okay, so then what we figured this out a while ago, but we're still confused about what this method is doing in the approximate case. But it is very interesting. One thing we can observe is by looking at the fixed points of this scheme for kind of general rank. So here we assume that the tensor rank is greater than the rank of the decomposition we're looking for. And what we can do is to actually look at the pseudo-inverses of the factors. Here I'll denote those by un for the an factor. And in a sense, in the iterative scheme, we're kind of multiplying by them. And then for the result, we should get back our factor matrix. So these are kind of necessary and sufficient conditions for the stationary point. So for the fixed point of our scheme, we can pre-multiply them to get kind of a reduced set of conditions. So if we pre-multiply by the pseudo-inverse, and now we get rid of the one variable we had that was an actual factor, and we're left with these pseudo-inverses of approximate factors. And so these are the equations that they must satisfy. And we can actually rewrite these in an interesting way that kind of suggests that these are, in a sense, orthogonality conditions. So in particular, if we think about the function associated with the tensor, so the multilinear function that takes as input vectors and, in a sense, takes the product of each element and the respective vector elements, so kind of tensor times vector along all modes, which is kind of, in a sense, the standard multilinear function we would think about with a tensor. Relative to that function, what these conditions can be rewritten in the following way. So we feed in the ith kind of row of u, the pseudo inverse, for each one of the arguments, and we feed in the jth for the remaining one, and this should be equal to delta ij. So for the ith row of the pseudo inverse of the approximate factor, it should, in a sense, give 1 when multiplied by a vector that's equal to the product of x and all of these u factors. But if we consider a different row of that pseudo inverse, it should give 0. And this generally, it's hard for this to be the case unless u is close to orthogonal or, in a sense, is well conditioned. And so in the approximate case, what we see is that this method tends to lead to very well conditioned decompositions, although they don't necessarily minimize the residual. And at a stationary point, they satisfy these conditions, which to me is kind of surprising that you can even necessarily find a set of vectors for which this is true. But overall, these are, for an order 3 tensor, 3 r squared equations, and we have a total of 3 times s times r variables. And what we find that is, even if the rank is quite large, so we tried, for example, an 80 by 80 tensor with a rank 600 true decomposition, and did a rank 70 approximation. And these it converged to a stationary point where these equations were kind of satisfied to the 10 to the minus 15 accuracy. So it seems that such stationary points, such fixed points of this iterative scheme actually exist, perhaps for general rank. Although we don't know how to prove that, and we don't actually know how to prove that we'll actually even locally converge to any type of fixed point in an approximate case. This is all still open for us. The way we actually got to this method, and a different way to think about what it's doing in the approximate case, is as trying to minimize a generalized distance metric. We can think about it as kind of looking at the residual of the decomposition and projecting it, if you will, although this is not an orthogonal projection, onto C dagger and B dagger, which have the same span as the quadratic product of BC. And in a sense, we can also think about it as minimizing both the projection onto the Kronecker product of these, as well as the projection of onto the quadratic product, because only the quadratic product part will actually be kind of in the span of the alternating subproblem. And we originally were working on trying to make a method designed by Artem and Afshar for minimizing residual in the decomposition based on Wasserstein distance metrics to be faster. And so the method that Nabjit proposed to do this was this, what we might call alternating Mihalonibus distance minimization, where in a sense, we want to think about this as a type of norm, and also extend this to have A, and then think about this as a subproblem of a more general problem that actually unifies all the factors. So here we're minimizing a loss function that's defined by this SPD matrix M. And if we kind of think about this as an inverse of some matrix, we get something that's closely related to what's known as Mihalonibus distance. But we are making a particular choice of M that's associated with our factors. And the important term here is this one. So it's the product of A of the factor and its transpose. So generally, this may be low rank. And so we need to augment it with something that just ensures that M is full rank, so we can invert it. And so the method is well defined with this as being a distance metric. But in fact, when we consider a subproblem, only this part of the distance metric actually affects it, because this part of the distance metric is essentially outside of the span of the columns of the linear system. So in a sense, we've kind of chosen a distance metric that takes into account the magnitudes of the different components of A, right? And so in what sense are we minimizing this? Specifically, we're minimizing this in the sense that we take M to be whatever is the state of the current factors, and then we minimize kind of Y, our choice of Y relative to one of the factors for that M. So we do not actually optimize the form of M at the same time as the form of the decomposition, but we will update M once we update Y. So in this sense, it's not immediately obvious that this is really what the method is minimizing, but in some sense it is. And you can also see that minimizing this will, in some sense, give well-conditioned decompositions as well. So somehow this regularization makes all of the makes the terms in the residual associated with different rank 1 components more equal in the way they contribute to the loss function. We can also extend this method from this point of view of Mahalanobis minimization to, in a sense, interpolate between standard ALS and this new alternating update scheme. And in doing so, we'll then hope to try to find a decomposition that is both well-conditioned and accurate. And if we want to reproduce standard ALS, all we have to do is essentially make M the identity. So what we can think about is, in a sense, to make M something that keeps a bunch of the singular values of A, of the factors, and inverts them, but kind of sets the other singular values to 1. So in a sense, this is kind of a regularization of our pseudo-inverse. And then solves kind of and if you do kind of minimization with respect to this, what you get is a system that you have to solve that's associated with the remaining singular values that we haven't inverted. And that's, in a sense, exactly the system that you need to solve in alternating least squares. So kind of these equations provide a general kind of statement of the method for an arbitrary M that can be written as a Kronecker product of these M sub k's. And so this allows us to kind of tunably reduce between doing ALS and doing this new type of optimization. And so if we try to do that for a tensor that's fairly ill-conditioned but has an underlying model plus noise, we can try to compare what the baseline mnor method does in terms of fitness and in terms of condition number relative to the standard ALS method, which is the blue line in both cases, and the hybrid version is the red line. And so as we see, the green line stays extremely well conditioned, but is not that high in fitness, although it does achieve some reasonable fitness. And here we compare the error to the actual underlying model, and we consider kind of performing ALS under like underlying model that's excluded the noise, as well as doing ALS on the noisy model. While for the hybrid method, we again consider both types of variance. And we see that kind of the hybrid method is capable of achieving the same fitness as ALS for relative to both the underlying model and kind of for the noisy case, while maintaining a much lower condition number. And so the condition number we measure here is from the paper by Breiting and by Neuwenhoven, which is actually a fairly kind of complicated measure to compute, but is kind of formally a good measure of how well conditioned the overall CP decomposition is. A more basic measure is just to look at the condition numbers of the computed factors. And we also generally do very well in that measure, which may be tied to the orthogonality conditions that have to be satisfied by the stationary point. But you can also kind of derive by just looking at the iteration that's being performed and arguing that it's better conditioned. And so that's kind of all I have on the method, except to state a bunch of open problems. So I mentioned kind of these stationary points, but we don't have a proof that it actually converges to anything in the approximate case. So when the rank is not equal to the true rank, although we observe it in practice that it generally converges to a stationary point for just about any tensor after some time. There could also be other views that lead to this method. We can think about it as critical points of the inner product of the tensor and the decomposition obtained by the pseudo-inverses. So this term is actually always fixed to be equal to R throughout the method. And in a sense, what we're optimizing can be thought of as this term, although what we're doing is just finding critical points and not necessarily maximizing or minimizing this. This term can be decoupled into the sum of the trace logs of these respective Kronecker product of terms. And the trace log is the same thing as a log determinant and is the same thing as the sum of the logarithms of the singular values of u in this case. So it's an interesting function, but it's not obvious that this view is that useful. One can also think about this in terms of doing a series of nested least square solves. So we've applied this Cauchy-Rao product of pseudo-inverses, but we can also think about the method as kind of applying the Kronecker product of the pseudo-inverses and then taking the trace. And the Kronecker product of the pseudo-inverses, we can now decouple into kind of two linear least squares problems that we, in a sense, solve by fixing one factor and then finding the best remainder for the decomposition, and then fixing the other factor and finding the best remaining thing relative to what we just computed. And you can also kind of commute these two steps, so you can kind of first optimize relative to C, then to B, and you get the same result, which is, I guess, healthy. And after this, in a sense, we're taking the trace to actually obtain our approximation, since C is a third-order tensor. And as I mentioned, kind of overall, the update rule, you can also kind of analyze and see is better conditioned, but we haven't quite quantified the degree to which this is the case. But it maybe perhaps we argue that this left inverse of a Cartesian product B is perhaps better conditioned relative to perturbations in A and B than the pseudo inverse of this object, which is kind of taking a pseudo inverse of the product of two things. Yeah, we're working on trying to release a draft of this this week, maybe submitting to Arxiv as late as later today. But I'm happy to answer any questions now, and these slides will appear on my website as well.
Thank you very much for the talk. So if anybody has any questions, please raise your hands or make yourself identify yourself in the chat. There was a question earlier by Daniel Kressner. I don't know if you want to ask it again. Your PhD student answered it, but you could just answer it yourself if you want. Daniel?
Okay, hi Edgar. Yeah, so that was essentially answered. So I was just wondering, in the ALS, when you use sketching, whether you would use the same random sketching matrix in every iteration, or whether you have to choose independently sampled sketching matrices for every iteration, in particular when you want to prove some things.
So for example, for leverage for sampling, I think you would have to do it at every iteration because the factors are changing. For tensor sketch, I would have to think and look back at how things work, but probably as well. Yeah, I think that is how things would work out.
Thanks. I don't see any more questions, and I also see we are past the 5 o'clock hour. So I suggest we, I can wait a bit more, people typing, but I don't see anything. So I suggest we thank Edgar again. Thank you very much. And oh yeah, I'm going to announce the next talk. Hopefully you can. You should be able to see the slides, hopefully, not the slide, but the website. So after this week, we take a 2-week break as usual, and the next talk will be given by Bunny Novarini in 2 weeks' time, and he hasn't submitted a title and abstract yet. But we hope to see many of you again in 2 weeks' time. So thank you very much. Thank you again, Edgar.